I'd like to spend the next half hour or so talking about how we can develop software components for Cortex-M microcontrollers, and also how we can reuse code from projects in new designs. When the Cortex-M processor was first launched in about 2006, ARM also started working with a number of their partners, so silicon vendors and also tools vendors, to define a set of standards that would make C code portable between different development tools and to a certain extent between different microcontrollers. So this is called CMSIS, the Cortex Microcontroller Software Interface Standard. And there's a number of specifications that make up CMSIS. And for our interest today, some of the key ones are CMSIS Core. So this specification standardizes the way that C code talks to the Cortex processor. There's also CMSIS RTOS that provides a standard API for small footprint operating systems, and a further specification called CMSIS Driver that defines a standard API to talk to common peripherals within small microcontrollers. So particularly, particular interest is CMSIS Driver. This typically targets communication peripherals that are common to many small microcontrollers, and this allows blocks of middleware, so TCP/IP, graphic systems, file systems, to have a standard API to talk to these low-level peripherals. So this means if you write code once to use the CMSIS driver, you can then reuse it on any Cortex microcontroller that provides a CMSIS driver. So this allows us to make a software component that uses these CMSIS standards, so we can talk to the Cortex processor with CMSIS Core, we can run in a small footprint operating system with CMSIS RTOS, and we can talk to some key peripherals via CMSIS driver. So this allows us in effect to completely abstract our code from the microcontroller, and it's also toolchain independent as well. So once we've developed our code to use these CMSIS specifications, we can then move it onto any other microcontroller that supports those standards. There's also an additional CMSIS standard called Software Pack, and this allows us to bundle up the software component so that it can be transferred and installed into a tool chain. So the CMSIS Pack is really a delivery mechanism for software components, and in effect it's really just a zip file which contains the software components that we want to transfer, if they're C source files, library files, object files, or even binaries. And it contains one additional file, which is an XML file that's used to describe the contents of the software pack. So these software packs can be installed locally, they can be held on a company server or web server or an intranet, or they can be put onto a cloud server so that anybody can download them and install them into their toolchain. So there are a number of use cases for these software packs. Today the most common use is one called a device family pack. So this provides all of the support files for a given family of microcontrollers. So things like the startup code, the header files, flash programming algorithms, documentation, etc. So when you want to work with a particular family of microcontrollers, you can download it and install its device family pack, and then you have everything that you need. And this is really the key to supporting a large number of devices. I think nowadays there's in excess of 3,500 different Cortex microcontrollers. So a standard tool chain using a traditional way of supporting devices just doesn't work anymore. Alongside the device family pack, we also have a pack that's maintained by ARM, the CMSIS pack. So again, as the standards are changed or new standards are added, we can download these and easily upgrade our tool chain. Aside from supporting the microcontrollers directly, software packs can also be used just to transfer just raw middleware or board support packages as well. So again, if you're developing a board that you're going to give to third parties, you can make a supporting pack, or you can develop a standard library and bundle that up as a pack as well. And also, as a developers, from our interest, we can develop in-house packs as well. So we can take code that we've developed, that we've designed in one project, and we can bundle that up as a software pack, put it on an in-house server, so that then any developers can download, install, and reuse that software. So again, if you start to work this way, over time it becomes quite a powerful technique to speed up development. So the CMSIS Pack is an open standard. Currently it works within the Kyle MDK ARM, but there's now also a plugin for Eclipse, so that it will work with open source tools as well. And there's also a number of other commercial tools vendors that are looking to adopt the pack system as well. So this, hopefully over time, will become a standard way of supporting Cortex-M microcontrollers and distributing and sharing software to work on those devices. So the way that this actually works within the Kyle tools, there's a separate standalone utility called the Pack Installer. This connects to a cloud server so that we can view all of the available packs for given microcontrollers, support packages for boards, and also general supporting middleware packages as well. We can then download those and install them into our toolchain. We can also maintain the versioning of these packs as well through the Pack Installer. Once a pack has been installed into our toolchain, there's a configuration utility called the Runtime Environment Manager. This shows us all of the available components for our particular microcontroller, and here we can then select these and add them to our project. So this isn't a code generator, it's really just a configuration utility. And it's reasonably intelligent in that if we select that we want a TCP/IP stack, then it knows that we have to have either an Ethernet driver or a UART driver if we're going to use SLIP or PPP. So it helps us to build a correctly configured platform and add all of the necessary files to our project. So then we can start writing our application code with an API provided by our underlying platform. So again, this allows us to rapidly set up and configure our project. As I mentioned, there's also versioning. So as different packs are upgraded, we can view the different version numbers. We can either tell the tool that we'll just use the most up-to-date version, or we can fix the version number of the component that we want to use. So again, a repository within the toolchain keeps a history of all the different versions, so if we upgrade and it breaks our code, it's then easy to roll back and rebuild our application. Now, to bundle up our software into a pack so that we can easily distribute it, we can create these with a number of simple low-cost or free utilities. As I mentioned, the pack is really a zip compressed file, and here we can use 7-zip, which is an open source free to use compression utility. We also need some form of XML editor, so something like Notepad++ or something like that. Within the toolchain there's also a schema for the pack, and there's pack documentation and a number of app notes that are also available on the Kyle website. So there's a number of simple steps to create our software pack. First of all, we need to produce some input. So this can be a stack or a library that we've written specifically, or it can be code that we've developed in one project that we just want to bundle up and be able to reuse later on. We need to then organize these files into a logical directory structure, and then we need to create our pack description file. So this is the XML file that is used to describe the contents of our pack. Then finally we have a simple pack generation utility which will examine the pack description file against the files. If it decides it's okay, it will then create our pack for us, which will then be ready to use. So a few simple steps to create our software pack. So in this example we're going to look at how we can reuse some code and make a component, and in this case we have a simple external GPS receiver that interfaces onto our microcontroller via a USART. We're going to read serial data in the form of an ASCII string which is in the NMEA protocol, and our code is going to run as a simple RTOS thread and communicate to the GPS receiver through the CMSIS USART. And then all of the data that we get from the GPS receiver is made available through a global structure that can be read via a set of helper functions. So we'll talk through this, and this actual component you'll be available to download and have a look at how all of this works later on. We'll send you out the link for this later. So the actual component is made up of a number of files, a C file for the actual GPS thread, a header file that provides the API to the rest of our application, another header file which holds all of the configuration options as hash defines, and then a simple user code, a sort of skeleton code of how to actually talk and get data from the received GPS data. So a simple component that demonstrates how we can create a pack and add this to our development environment. So we have produced our code and our input. We now need to organize these files in a logical structure. So this is completely arbitrary. You can set it up however you want, but here we have directories for the component source code, the documentation, examples, and also the license information as well. And then underneath that I have a separate directory for the GPS code, so that if we want to add other components we have a structure that we can easily expand to accommodate future components. First two steps, nice and easy. Now the next stage is to create the XML file which describes this pack layout for the development tool. So above our directory structure we first of all have a template of this pack description file, so this vendor.pack name pack description file. And then we have the utilities, the packgen.bat, which is actually going to be used to create our reusable software pack. So first of all we need to rename that template to name our component. So we have the vendor name is Hitex, and we're just going to call this our software components pack description file. And then inside this pack description file, it's an XML file with a number of containers so that we can describe our pack. So we can describe the software component, we can describe some rules, some conditions on how it's going to be used and the dependencies of our files. We can also provide information about boards that it can be used on and extend this for various board support packages. And it's also, if we want to, we can provide examples so that users can easily see how our code can be used. And then we can also provide information about the devices, so Cortex processors or actual microcontrollers that are supported by this pack as well. So first of all we have a header that we need to edit. So in here we can set up the vendor name and the name of the pack, and these must match the actual file name of the pack description file. We can also provide a URL where the pack will be maintained. So once this pack's installed, when we start the development tool, it will check this location to see if there are any new updates. So if we publish a new update, it will actually be pushed out to our users automatically, and they can, if they want to, download and start using the new version. And then finally, if you're brave enough, you can provide a contact email so that your users can, can get in touch with you. Now, we have our managed runtime environment, which has a number of standard sections in it. However, these might not match our software components. So within the XML file, we can actually extend these sections, and here we can create a new section for our called components that will hold our software components. Next thing we can do is to start to describe the files that are used in our software components. So within the XML file, there's a component section. Here we can define our software component, so we say that it wants to go into the component section, subgroup called GPS module, and then a subgroup for our specific GPS module that we're supporting. Underneath that, we can give a description, and then we can nominate all of the files that are going to be part of our component. So we have a source file, the GPS thread, and then a couple of header files that are going to be added to the project as well. And on the final header file, the configuration file, we've given this the attribute of config. So this means that this header file will actually be copied into our project so that we can edit it, whereas the previous two will remain in the toolchain like library files, so that they're within the version of this software component, so we don't edit those, and they're not actually physically copied to our project directory. So there are a number of different file types that we can add, so object files, source files, utilities, script files, etc. So it's a fairly flexible scheme that will support a wide range of software components. Once we've done that basic description, we can create an initial software pack. So here we can just run the the gen pack utility, and this will then create us our Hitex components version 1.0.0 pack. If we then double click on that, it will install that pack into our toolchain. So now once we've installed this, within the runtime environment, we now have our components section, our GPS section, and then support for our GPS receiver. When we select the, this component, it will then be added into our project. So here we have the normal sort of manila folders for our application code, and then our software components are the green diamonds that are holding all of our component files. So here we can see the GPS thread is added, and this has the yellow key on. That means it's a read-only file. And then the GPS config file that was defined as a configuration file has actually been copied to our directory so that we can edit it to configure the component. Now, that's very nice, but it's really just a pretty way of adding files to our project. If we go back into the pack description file, we can make this component a bit more intelligent by adding some conditions. So these are rules that describe the dependency of how of what support files are necessary to make this component work. So here we're creating a condition ID, and we're going to call it GPS dependencies, and we're telling it the other components that are required to make our GPS thread work. So we need a CMSIS driver, and we're using the UseArt driver. We need the CMSIS core specification, and we need the CMSIS RTOS specification as well. And then we can go back to our component description, and we can add this rule to our component description. So now when we rebuild and reinstall our GPS component, we'll have to obey those rules pardon me, to add the component to our project. So here we've now reinstalled the component, so when we select it, the selection column turns orange, and that tells us that we have to add some additional components. And then in the validation section underneath, it tells us what components are necessary. So we need a UART and we need the operating system to be added. And then we can add this component to our project, and the platform is correctly configured so that we can start using it. There's also, as I mentioned, versioning. So within the software, the pack description file, there's a released version. So each time we do a new release, we need to increment this, add a comment if necessary, so that as the different versions are installed, we can view them within the pack installer or within the runtime environment and select which version we want to use. It's also possible to add examples. So again, here we have the examples container within the pack description file. We can add an example for our GPS component, and then we can nominate the board that it's going to be used on and the project file name. So now within the pack description file, we can click on the MCB board that we're using, and then in the examples tab we can see that there's a GPS component configuration example which we can then copy and have a look at this example project. And this is quite handy in that we can muck around with that example, edit it, change it and experiment with it. But then always within the tool chain there's a pristine copy that's held for us that we can refer back to at any point. So you don't have to worry where you left that zip file, it's always easy to find. We can also expand the different file types within our component, so we can also add a documentation file as well. So here when we add the documentation file, the description column turns up as a link, so we can click on it here and it will open up the documentation file. We can also, another useful feature that I think people using this system may tend to overlook, is that we can add template code as well. So these are useful fragments of code which can be added to our project to speed up development by a user. So here we've added a simple template that gives us the initial setup to start using our GPS component. And when we go into add a new file to our project, at the bottom there's user code template, and here we've now got this template available which we can click and simply add to our project as a bit of example, as a bit of skeleton code. Now, I mentioned earlier that we have our header file which has this configuration attribute. So this will add the file to our project, but these configuration files are also can also be coded up with XML tags that make them easier to view and more intuitive to configure. So really these files are just C source code, so it's possible to view them in a normal text editor and edit them. But by using this tags in the comments, we can have a configuration wizard which then allows us to graphically edit and modify these hash defines and really see what they mean and provide tooltips and help comments, etc. That allow our users to very quickly understand and configure the system. So the first time you make up one of these files probably takes about half a day or so. But once you get used to it, it's quite easy to construct them. It's sort of cut and paste and change the text, so you can build these things up quite quickly. So again, there's a simple, a limited number of tags that allow us to view, modify, and enable sections of our configuration header files. So here on our GPS configuration file, we're selecting what GPS sentences we want to receive. We're also selecting the UART that we're going to use and the baud rate that we're going to use as well. So again, this can be done very quickly and intuitively when a third party comes to use this. So so this allows us to easily create a pack. So once we've created a pack, that can be directly installed, so you can give it to somebody as on a USB drive. We can put it on a local server or a company intranet, so it can be held within our organization, and then that can be maintained by a development team. If you want a wide number of people to serve it, it can be placed onto the Kyle Cloud Pack server, so that is then available to a large number of people. So if you are if you want to share your software or you're making commercial software, this exposes it to a large number of people. It's also possible to make packs that contain examples of finished products as well. So this is a great way to expose your software to a large group of people. It's free to place your software packs on this cloud server. It just has to be tested by Kyle, and then it can be freely published. So CMSIS Pack is a very easy way to reuse code. It has simple version and configuration control. Really, it's all just source code, so there's no complex case tool on top. It allows, but above all, it allows the easy distribution and sharing of software, and it's a great way to collaborate and distribute software over the internet. So I'd like to thank you for listening for this today.